Welcome back, grade 12. Now we are continuing with our galvanic cell. So now we are doing part 2. We have done part 1, so we are continuing to part 2. So we have a question here on the galvanic cell. Now remember the first question, it was in a diagram form, but this one is like in a table form. So it's a different style of assessing the galvanic cell understanding of the learners. So you must be prepared to see something that looks like this, like a table. So the question now said, question 6, batteries consist of one or more galvanic cells. A galvanic cell is a combination of two half cells. So they said John wants to determine which one of the option A or B shown below can be used to assemble a galvanic cell with the highest potential difference. So you can hear from the statement that John has two options, option A and option B. So he wants to know between option A and option B, which of these two combinations will give him the highest potential difference. So before we go to the questions, let us look at the table and see what is going on here. So option A, which is this one, they said that you have the silver in a solid form, which is an electrode, and you have an electrolyte of AgNO3 in an aqueous solution. Another cell has nickel in a solid form, and you have a solution of nickel NO3 too in an aqueous solution. So I think let us give a picture of this on the side, and then we draw a picture of the second cell, which is cell B, so that we can be clear as to what is happening here. Okay, before we go and draw the sketch, let us look at the second cell, which is cell B. They said we have the magnesium, which is an electrode. The solution is magnesium nitrate in an aqueous solution. Then you can see the second cell has silver, which is an electrode, and the electrolyte is AgNO3, which is silver nitrate. So I'm going to draw these two cells, and then I'm going to put on the information so that you can have a clearer picture as to what is going on. Okay, so yeah, I've tried to draw the two cells. You can see the first one, which is the galvanic cell A. The first cell on the left, the electrode, the electrode is silver. Then you can see the electrolyte there is silver nitrate. This is the solution inside that first beaker. Then we have the nickel, which is a second electrode. And then the solution inside there, it is this nickel nitrate. Then for galvanic cell B, the electrode is Mg, which is in the solid form. This is Mg. Then the solution inside the first beaker on the left is MgNO3. So that's the first one. The second one is Ag, which is an electrode. Then the solution inside there is AgNO3, which is silver nitrate. So on this side, you have magnesium electrode and the magnesium nitrate, which is a solution. So these are the two cells. So this person called John has to choose now between option A or option B, and to check which of the two cells will give a higher potential difference. That's what that statement was saying. So let us go back to the question and see now what we have to do. Okay, so let's look at question 6.1. Question 6.1 says, draw a fully labeled diagram of the galvanic cell that John can use to measure the potential difference for the cell in option B. Use positive and negative sign to indicate the positive and negative electrodes respectively. So they say now we must draw this galvanic cell in option B. But they said that for the electrodes, which is magnesium, and the one for silver, we must indicate which one is positive and which one is negative. So we have to go back now to this. I've already drawn the electrode in option B, but now the challenge is I did not indicate whether the magnesium is positive or negative or the silver is positive or negative. So we need now to indicate which one is positive, which one is negative, the electrodes now. So how are we going to do that? Okay, first let us look at the electrolyte. This one, the magnesium nitrate, that is the electrolyte, the solution. So if you look at the electrolyte here, just want to give you a picture. So you have this magnesium nitrate solution. So if you break this down into a positive ion and a negative ion, you will know that the magnesium was a Mg2 plus ion, and it was reacting with the nitrate, which is NO3 minus. So when these two react from grade 9, you know that this 2 plus means that this magnesium needs to donate 2 electrons to the nitrate, and the negative on the nitrate says I need 1 magnesium atom. So that's why in the product you're going to have MgNO3 2, meaning that the magnesium did react with 2 nitrates. So this thing is like Mg2 plus wants to react with a nitrate and another nitrate, so that these two can be donated there, another electron can be donated there. So this is what we know from grade 9 or grade 10. So what I want you to notice is that in this solution, that means that we have Mg2 plus ions in aqueous solution. Similarly, if you look at this one, which is AgNO3, if you break this down, that means this was Ag plus and 1 NO3. So that's why you're going to have one of these donating an electron to one of that. So the product will be just 1 silver and 1 nitrate. So that means that inside the solution you have here the Ag plus. So that's what I wanted you to notice. So we're going to look now for the Mg in a solid form with Mg2 plus in an aqueous form, and Ag in a solid form and Ag plus in an aqueous form or in an ion form. So we're going to go now to the table 4b, the table of reduction potentials, and then we're going to look which one has a higher potential, which one has a lower potential between Mg and Ag. Okay, so this is table 4b, and now we are looking for Mg. So we look for Mg, we'll look for Mg. Okay, here is Mg. And the potential there, the voltage there is negative 2,36 volts. As you can see, that is Mg2 plus, receiving 2 electrons to become Mg in the solid form. Now let us look for the second one, which is Ag, which is the silver. So we're looking for the silver. Okay, we find it there at the bottom. This is the silver, Ag. it has a potential of positive 0.80. You can see there is Ag plus 1 electron to become Ag, which is in a solid form. So we saw now that the Mg reaction is above and the Ag reaction is below. Here is Mg above, here is Ag below. So I'm going to take these two reactions and then I'm going to write them in a separate piece of paper. Okay, so this is the format that we use. So we write the arrow downwards on the left and set oxidizing agent. Then we write the arrow looking or pointing upward, and then we write a reducing agent. And then you saw that the first reaction was the magnesium reaction with a negative 2.36 volts. Then the second reaction was the silver reaction, Ag plus 1 electron to give us silver, which has a positive 0.80 volts. So this is how these reactions, they were like this. The one on top, magnesium, the one below, which is silver. So you know what we do. We want to find out the movement of electrons. Electrons moves from the region of lower potential energy to the region or state of higher potential energy. So the one that is low potential is this one, the negative 2.36. Which one is negative 2.36 is the magnesium. Then the one that is higher is this one, silver, which is positive 0.80 volts. So this one is silver. So we know that if electrons are moving from negative to positive or from lower to higher, they are moving away from the magnesium. In other words, the magnesium is losing electron, and we know that losing of electron is called oxidation. Oxidation is loss of electron. And the silver is now receiving or gaining those electrons. We know that reduction is gain of electrons. So oxidation is taking place on the anode. Anox oxidation takes place on the anode. So that means this one is the anode. Then the gain of electrons is called reduction, and reduction is taking place on the cathode, red cat. So this side now is our cathode. That means that the magnesium, you look, the magnesium is above. We said the one that is above is our reducing agent. So this one we know is our reducing agent. Then the one that is below, this arrow is pointing below, is pointing at silver. So this one, silver, is our oxidizing agent. So we just wrote all the information that we needed. So we know that the magnesium is a anode and it is a negative electrode. The silver is the cathode, and then it is a positive electrode. That's what we wanted. Which one is negative, which one is positive? So magnesium is negative, silver is positive. So we go back here, we said magnesium is negative and the silver is positive. So we know this one is our anode and we know this is our cathode. So if you remember the question was saying draw a fully labeled diagram of the galvanic cell that John can use to measure the potential difference for the cell in option B. Use positive and negative sign to indicate the positive and negative electrode respectively. So we need to use which one is positive, which one is negative. So that's what we have done here. We have said the magnesium is negative and the silver is positive. So you are just required to draw only this. You are supposed to draw this cell. That's what you are supposed to draw. So we are done now with this question. We are looking now at the following question, which is 6.2. 6.2 says write a balanced chemical equation excluding spectator ions for the net or overall cell reaction for the galvanic cell in option B. So now they want the net overall cell reaction, and we can exclude the spectator ions, which means that you remember these ones, we call them spectator ions. This one is the spectator ion, so we exclude those ones. So we're not interested in the spectator ions. So let's quickly write these two half reactions, and then we write the net reaction. Okay, let us come back here to this page. So remember, we said here magnesium is the reducing agent, and what is taking place on the side of magnesium is oxidation. What is oxidation? Oxidation is the loss of electrons. That means magnesium is losing electrons. So if you look at this half reaction of magnesium, that means these two electrons are supposed now to be on the left. So I'm going to take all of this that is on the right, that is on the left, and put it on the right. These two electrons are supposed to be on the right. This Mg in a solid form is supposed to be on the left, because on the magnesium, electrons are being lost. Then on the silver cathode electrode, we know what is happening there is reduction. What is reduction? Reduction is gain of electrons. That means on the silver, the electrons are supposed to be on the left because they are being gained. And then we must change this double arrow to a single arrow, the double arrow to a single arrow. So that's what I'm going to do now. Okay, yeah, here is a oxidation half reaction. So we have Mg in a solid form, double forward arrow, then we have Mg2 plus 2 electrons on the right because electrons are being lost. There's oxidation taking place here, and Mg is the reducing agent, but it is being oxidized. Then the second one is the silver one. You can see there's a gain of electrons there, and it becomes the silver in a solid form. So this is the reduction reaction. Silver is being reduced there. It is an oxidizing agent, but it was reduced. So now I'm going to take these two reactions and write them on a separate space. Then we have to write now the overall net reaction of these two. So these are the two reactions. So the first one, we know this one is oxidation, and the other one is reduction. So we need now to react the two. You can see that magnesium is donating 2 electrons, but silver is gaining 1. So we have to first balance these two reactions. So we cannot now cancel the uneven electrons. So we need to multiply everything here by 2. So if you multiply everything by 2, this is going to become 2, this is going to become 2, this is going to become 2. So we multiply everything by 2. So now our equations, half reaction, are balanced. So that means that these 2 electrons now cancel out because they were donated that side, they were gained this side. And then what is left now on the left, which is Mg solid form, plus 2 Ag plus, which is in the aqueous form, forward arrow. What is left on the right will be Mg2 plus in an aqueous form, plus 2 Ag in a solid form. We call this now the overall, we call it the net overall cell reaction. So this is what they were looking for, the net or overall cell reaction. So this is how you write your overall net cell reaction. So we are done. It's not a cell notation, it's an overall cell reaction. So this is how you write it. You ignore the spectator ions. So we are going to now move on to the next question. Now the next question says in 6.3, calculate now the initial potential difference that can be obtained under standard conditions for the galvanic cell in option B. So they want us now to calculate the initial potential difference for the galvanic cell in option B. Okay, so I'm coming back now to this page. So the formula that we are going to use says E cell is equal to E cathode minus E anode. So which one is the E cathode? The silver was the cathode, and the potential difference there was 0.80 volts minus the one that is anode is the magnesium, and the potential difference there was negative 2.36. So we punch this in the calculator. So we have 0.80 plus 2.36. So the answer that we get is 3.16. So remember, this is 0.80, negative and negative, it's a positive, 2.36. So the answer we said it's 3.16. 3.16 volts. So this is the initial potential difference of this cell, which is the cell B, is 3.16. So I'm going to put it here for this one. The E cell of this one is 3.16 volts. We don't know the one for option A. We know the one for option B. So we are going to 6.4 now. State 2 standard conditions that John must adhere to during the experiment to ensure that the measured potential difference is the same as the calculated potential difference. So we just need to write 2 standard conditions. We said that we have 3 standard conditions. The first one, the temperature must be 25 Celsius degrees or 298 Kelvin. The second condition says the concentration of the solution must be 1 mole dm cubed. Okay, so you can choose, you can take the first 2. You don't have to write the one for the pressure because we are not dealing with gases. This condition is mostly relevant for gases. So you can take the first and the second one. Okay, now I'm going to 6.5. Write down the cell notation or symbolic notation for the galvanic cell in option A. So they want now the cell notation for the cell in option A, which is this one. So the one for silver in the silver nitrate and the nickel in the nickel nitrate. The cell notation there. Okay, I think the answer for 6.5, the cell notation for the cell in option A, we have done this one in part 1. If you remember, in part 1, we were dealing with the cell that looks exactly like this in option A. So that cell with the Ag on the side of the, was it the anode? Then the nickel, which was on the other side, this was Ni2+. I think it was the anode, this one, and this one was the cathode. So we did write the cell notation in video part 1. So just go to video part 1 and check how to write the cell notation. For the purposes of time, let me not repeat the same thing. So it's the nickel in a solid form / nickel 2+ ion in an aqueous state. Then don't forget to write 1 mole per dm cubed double / which represents the salt bridge. So this is the salt bridge. Then on the other half cell you have Ag+, which is a silver ion in an aqueous state / don't forget to write 1 mole per dm cubed again / then AGS, which is a electrode for the silver. Yeah, I did explain how to get to this in video part 1. I'm not going to repeat it again. So let me do now the last question, which is 6.6. They said now, without any calculations, determine which one of option A or option B should result in the galvanic cell with the highest potential difference. Refer to the relative strengths of the two reducing agents involved, as well as the relative strengths of the two oxidizing agents involved to explain your answer. Okay, quickly let us look at the table 4b for the nickel. Well, remember we said nickel is negative 0.27 and the Ag is positive 0.80. So this one is negative, this one is positive. So this one we know is our cathode. This one we know is our anode. So this is E cathode minus E anode. So this is positive 80 minus 0.27. We got the answer to be 1.07. We did this calculation in video part 1. But now I just want to take this value, which is 1.07, and compare it. Remember, this is galvanic cell A, and compare it with galvanic cell B. Okay, so this is cell A, and that is cell B. Now I want us to look now at the potential differences of the two. E cell for option A is 1.07. The one for option B is 3.16. Now the question was saying, without any calculation, determine which one, option A or B, should result in a galvanic cell with the highest potential difference. So without any calculations, I was just trying to show you by calculation, option B has the bigger potential difference. But now, don't look at the calculations now. Let's just look at the cells, both cells, and then try to make our deduction now to arrive at the answer. Okay, so by looking at these two cells, you can see that the silver is on the cathode for option A, and also the silver is on the cathode for option B. So silver is like acting as the same, which is receiving electrons. Remember, on the cathode we have reduction, and the reduction is a gain of electrons, which means that silver is a oxidizing agent. For both cells, silver is the oxidizing agent, which means that silver is gaining electrons. Now, if you look at the second, look at option A, the second cell, which is the nickel, which is on the anode. And then if you look now, the anode on option B is the magnesium. So this is the only difference. The anode of option A is nickel, and the anode of option B is magnesium. So we need to know now which one is a stronger reducing agent between the nickel and the magnesium. Because we already know that silver is an oxidizing agent in option A, silver is an oxidizing agent in option B, but the reducing agent in option A is nickel, the reducing agent in option B is magnesium. But which one between the two is the stronger reducing agent? Now, if nickel is a stronger reducing agent than magnesium, that should tell us that the potential difference of the cell is supposed to be higher than B. But if magnesium is a stronger reducing agent than nickel, then the potential difference of this cell is supposed to be higher than that of A. So that's the question that we are asking now. Which one is a stronger reducing agent? So we need to go to the table 4b and check again which one is a stronger reducing agent. Then we'll come back and make our conclusion on this diagram. Okay, here is table 4b. So according to the table 4b, you can see that the magnesium is there on the top and the nickel is here below. And remember, the arrow on the left is pointing downward and saying oxidizing agent. the arrow on the right is pointing up and saying reducing agent, which means that the one that is above is a stronger reducing agent than the one that is below. So magnesium is a stronger reducing agent than nickel. Why? Because of it is at the top and the nickel is below. So the arrow is saying reducing ability when you go up. So this means this one is a stronger reducing agent than this one. So we have answered now our question, which one is a stronger reducing agent? It is magnesium. Why? Because it is above. The arrow is looking at the one that is above and saying it's a stronger reducing agent, which is magnesium. So let's go back now to that diagram and make the final statement. So now we have identified now the magnesium, this one, as a stronger reducing agent than that one. So because magnesium is a stronger reducing agent than nickel, then the conclusion is that the cell, which is a cell in option B, should have the higher potential than that of A. Why? Because the magnesium, or we can say because the reducing agent in option B is higher than the reducing agent in option A. That is the reason. So that is the end of our questions, because this one was saying refer to the relative strengths of the two agents as well as the two strengths of the oxidizing agents involved. Explain the answer. We did that. We say the one that is going to have a highest potential difference is option B. Why? Because it has because of the reducing agent in option B is higher than the reducing agent in option A. Yeah, we have done now this question. I think we will now look at the last type of the galvanic cell, which involves a gas. That will be on part 3. So now I will see you on part 3 of our videos on galvanic cells.